Okay, now we know the definition of that friction factor. It's not at 0.1, it's not at 0.2, it's at the average. Okay. So after I get this form, we do just change from kind of scientific form to engineering form to be in the unit that we like. Instead of mass flow rate, that we have the relationship between mass flow rate and standard cubic foot per day, right? But we need to know the specific gravity. Put everything all together, at the end, we get the form that easy to use, okay? Easier to use. But we still have this. 1 over square root of friction factor. Okay, 1 over square root of friction factor. And when we trace it back, that friction factor is not at 0.1, it's not at 0.2, it's an average between, it's just an average property, okay? And when we do this, to get this equation, it is for isothermal flow, and we make some more approximation. This form of Q sub G, okay, it is easier to use than the original form, right? The original form has pressure on the top one and on the bottom one. Okay. The equation, the isothermal flow equation that you see now doesn't have the natural log term. Okay. So instead of implicit equation, it becomes kind of explicit. So the assumption is 2 log P1 over P2 is a lot less than the friction term. Okay. So this friction term has to be a lot greater than that term. So that's the assumption. We have it over there. Okay, that's the assumption. So now we get the final form, isothermal flow equation. Okay. Now, how do we use it? Okay. Q is standard cubic foot per second. Okay. And when enter flow rate as the standard cubic foot per day, and L in mile and D in inch, we have blah 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 blah. So after do some conversion, we can have the length in the unit of mile, diameter in the unit of inch, and Q instead of per second it will become per day. Okay. GPSA use 38.77. So this is the form that we use. What you need to know is the unit. Okay. L sub m is mile. Okay. D is diameter in inch. Okay. They put everything else for us already. They put molecular weight of air, they put G sub C value, R value, pi value, everything is in. So we need to specify the base pressure, base temperature. Okay. Next, after Karim is Afshin, right? What is the unit of base temperature and base pressure that you want to use?
Fahrenheit and PSI.
I don't like Fahrenheit. Can we do something else other than Fahrenheit?
Kelvin.
Huh?
Rankine.
Rankine. Yes. Because that R value work for Rankine. Okay. And that R value work for PSI A. Don't just use PSI, okay? It has to be PSI A. And everything is PSI A and T is in Rankine. L is in mile, okay? Because we try to put it in unit of mile. 1 mile has that many feet, okay? 5,280. Okay, we have the equation already. One thing to look at is friction factor was assumed to not be a function of distance, okay? F was taken out from the integration early on in the derivation that we skipped. We know that rho u is constant for isothermal flow. Okay. Reynolds number is rho u d over mu, right? Rho u d over mu. We have rho u constant. We have isothermal flow. Isothermal flow means viscosity is also constant. Okay. What does it mean? What is rho u constant? Next option. Simon. Rho times u equal to constant. What does it mean?
Viscosity is constant.
What?
Viscosity.
Density multiplied by velocity equal to constant. What is the physical meaning of that? Constant what? Constant mass flow rate,
Yeah, mass flow rate.
constant volumetric flow rate, constant what?
Some mass flow rate.
Constant mass flow rate, right? U, if we multiply by A, will be U multiplied by A is volumetric flow rate. Volumetric flow rate multiplied by density equal to m dot mass flow rate. So it's a constant mass flow rate. When we have constant mass flow rate and we assume constant temperature, that makes viscosity to be constant too. Diameter is constant, so rho Vd over mu is constant. Then we have constant Reynolds number. Okay. When Reynolds number is constant, we have what? Constant friction factor. So this means it doesn't matter if it is friction factor in the front, in the back of the section, in the middle, they are all defined as the same Reynolds number. Okay, same Reynolds number. They are all the same. Okay, rho u. U will change with distance. Okay, rho also change with distance, but rho times u is constant. Okay, so friction factor is a constant. Next, we assume no compressor. We assume horizontal flow. We assume Z is not a strong function of pressure. Okay, so dz equal to 0. We don't need Z to be 1, but we just need to say that compressibility factor doesn't change much. Just that. It doesn't need to be 1, but the change of compressibility factor within that distance is negligible. Okay. Let's take a look at compressibility factor. Okay. So this is for gamma equal to 0.65. Compressibility factor, it can change quite a bit. Okay, that is a temperature of 25. But if we have like hotter, it may not change much. So this means this may not work all the time. Okay, depending on where are we at. To do it more correct, we have the expression, a quick expression to get compressibility factor. So Z average as a function of P average, okay, and temperature average. Okay. T is Röntgen, P is PSIA, and gamma is molecular weight over molecular weight of air. So for pressure less than 100 PSIA, that's a formula, quick formula to get compressibility factor. And pressure can be averaged by using this formula. Okay. Next to Simon. Demila, why do we need to use average pressure? P bar used where? Where do we use it? I give the formula, but where do we use it? I cannot hear what you say. Can you come to the podium?
No, what the question?
Come here, come here, come here. I cannot see what you say. Come here. Or speak louder. You want to speak louder? Come here, come here. What was the question? That's your question, right? The question is P bar. I give the formula to use it. Where do we use it? You see the formula for P bar, right? I give formula for some reason. Where do we use that? Which formula? Average Z factor. Thank you very much. You can go back. So that is to use for average compressibility factor. Okay. Although we know P1 and P2. For the case of rough region, we can get 1 over square root of F from just epsilon over D. Okay. Fully rough region means very high Reynolds number. If Reynolds number is not that high, we cannot do this approximation. Okay. If it's very rough, the friction factor will be just a function of roughness. Then it's reduced to just this form. Put that in, we have approximation equation. Okay. 1 over square root f is called transmission factor, and we have that formula for it. No, that's a different thing. This formula is for elevation term. Elevation term is typically very small, but if there's any, we can use that formula to do the calculation. Okay, final one. We rewrite everything and give out all the unit. Okay. Previously we talked about the isothermal flow, right? The equation for isothermal flow is this one. The next equation we try to go from isothermal flow, put some value for Z and friction factor, and try to derive this Weymouth equation. Okay. To derive the Weymouth equation, we put everything together and we assume fully rough region for the friction factor. Okay, that's a key word. Okay, Weymouth equation we assume fully rough region, and we have E, capital E, transmission efficiency, pipeline efficiency factor between 0 and 1. Okay, so we end up with Weymouth equation. Weymouth equation is good for short pipe. Okay, degree of error increased with pressure must be fully developed turbulent flow. So that is short pipe. And fully rough region. Okay, that is Weymouth equation. So this means Reynolds number has to be high. Okay, velocity is high, Reynolds number is high, so it's used for short pipe in the facility. Do we use it in the facility Weymouth equation? Yes. So within the facility, the equation for pressure drop for single phase gas flow is Weymouth equation. Good? I can just ask you between Weymouth equation and Penhat equation, there's two formula. Weymouth equation is used for short pipe, high Reynolds number, fully rough region, yes. Short pipe, long pipe means from here to Louisiana. That's long pipe. Okay. Short pipe is in tank battery. Within the tank battery, use Weymouth equation. It's based on the measurement of compressed air flowing in a pipe from the diameter of 0.8 inch to almost 12 inches. It's for fully rough region. Okay. Friction factor is only function of roughness. Memorize this for the exam or quiz for high Reynolds number region. It should not be used if the diameter is larger than 1 inch. Good for short pipe with high pressure drop in facility, in tank battery. From GPSA, we have to know that multiply Q from Weymouth equation with 1 over square root of Z give the corrected Q value, which will closely approximate the metal flow. This is a suggestion from GPSA. Okay, in GPSA, hey, we need a little bit more accuracy, multiplied by 1 over square root Z. But this 1 over square root Z itself is not part of the Weymouth equation. Okay, if you want it accurate, use Weymouth equation. Use even more accurate, take GPSA suggestion multiplied by 1 over square root Z. Good? So Weymouth equation is for short pipe, fully rough region. Next one is Penhat. Yes.
So you say it's for short pipe and the length is in miles?
Yes, the length is in miles. High Reynolds number. Like for example, if I go from test separator to the tank battery, I should still use Weymouth equation. It's like small diameter. Long pipe means cross-country pipeline. Okay, cross-country pipeline. In cross-country pipeline, big diameter, deliver a lot, we use Penhat equation. We have Penhat A and Penhat B. Okay. The note here is it's become less accurate as flow rate go up. Okay. And originally it's from Penhat Eastern Pipeline Company, good for long cross-country pipe gas transmission pipeline, 12 inch and above. Today, the recommendation is use just panhandle B. Okay, that is Stuart textbook. So Renault number is 5 to 11 million. So basically, panhandle B is for big pipe, cross country pipeline. Okay, if your pipe from the 1 mile, it's not cross country yet, right? Use the Reynolds equation. For cross country pipeline, use panhandle equation. All the unit is given, okay. Pipe efficiency factor is between 0 and 1, and recommendation is 0.92, okay, 0.92 pipeline efficiency factor. You may use something else, okay, depending on OD and ID. So F from panhandle A multiplied by 0.92, then we can have the capital E. Okay. So here is the OD and ID of the pipe. And this column show F from panhandle A. That's a value 0.9, 0.9, 0.9, 0.9. Basically you use 0.9 multiplied by 0.92. Become capital E to use for panhandle B equation. And panhandle B equation look like this. Okay. Good. Brand new pipe. Okay. 0.95, 0.92 average, unfavorable 0.85. Okay. Unit definition is defined same as panhandle A. Okay, question. What's your name? Yes. Hamed. Okay, not Mohammed. Hamed. If I use the panhandle B equation, okay, and I use the first equation that we talked about, that first principle, the momentum balance equation, do we get the same answer? Yes or no? Identical answer. That's yes or no?
No.
No. Which one do you use? Panhandle or the equation I showed first?
First one?
Panhandle, okay, for cross-country pipeline. The problem with the first equation that we use, it doesn't consider the chain. It is difficult to put the chain on density or temperature into it. But that panhandle equation is consider everything already, okay? So this is more accurate. For the case of liquid, just use that first equation, okay? For the pure gas, use this, okay? Panhandle A and B use the preset value of gas viscosity. E may be adjusted to make prediction match with the middle result, then extrapolation can be done. In practice, panhandle B is used for straight line portion of the friction factor diagram, fully wrapped to. Neither Weymouth nor panhandle B or A give conservative assumption that can always over-predict the pressure drop. So when we get result from panhandle equation, it is not the extreme case. The actual pressure drop could be more than that. Okay? Low pressure gas flow. We use Oliphant formula P for the case of vacuum, and to bracket here mean from that value to that value. Okay, so we can use that formula. So Oliphant formula, and the formula is given. Good for pressure less than 35 psig. It is valid for that range. Okay, vacuum to 100, but if we have less than 35 psig and gamma above that, it will be even more accurate. Okay. Split glass formula. Pressure less than 1 psig at 60 F. So that's the formula. And in split glass, L is in feet, P is PSIA. So good result for delta P within 10%, less than 10% of P1, less small pressure drop. So there's all kind of equation to use. Your task is to memorize when to use what. Okay. And okay, last slide, selection method. Let me give you this first then. Sit one seat apart to do the quiz. One calculator, close book, close note. Put it face down. You don't see it yet, okay? You can write your name on the back. We will start at the same time. All gone. Raise your hand if you don't have it. You have a lot. You have a lot. Raise your hand if you don't have it. Okay. Raise your hand if you don't have it. Okay.
We're good over here.
Other than Mr. Bullard, anyone? We have 1, 2, 3, 4, 5 over there. Thank you very much. We didn't take enough from you. It is still 12:10, right? Let's finish the last slide. In general, Weber and Penhat use it. Select whichever give you higher pressure drop. Okay. Weber equation in summary is for small pipe, short run pipe in production facility, Renault number is high. Penhat is large pipe, cross-country pipeline. Okay. Use either these two. Select whichever give us higher pressure drop. Split glass is for low pressure vent for less than 1 psi. So if I have a pressure drop from like tank, okay, or the tank on the top has a vent line, they connect to each other. How much is the pressure drop in the vent line? I use split glass, okay. Or I can also use the Oliphant equation, okay, any of these. And this is just calculation thing. I think who doesn't have it? Everyone have it, right? Okay. In your case, does it match with this? Yeah, I think it's kind of match. Are you ready? We will not do anything yet. Okay. You want to take the rest of the time? Okay, let's take the rest of the time. I give you more than 5 minutes. Start, please. So it will be end at 12:20. Or you want to do just 5 minutes and more lecture? No more lecture, right? Once you are done, quietly stand up and leave the room. Please. Okay, quietly stand up and leave the room. Leave your test on the table. I'll go get it. think we have a lunch for the field trip day. It is on the yard back of this lecture room. Okay, that lunch. I will announce more tomorrow too. You just need to write your answer that you get from each iteration in scientific format, okay?